Thank you very much for this kind invitation, introduction. So today I will talk about our recent work on explainable AI. The main focus will be on methods. I will tell you I will explain you our method in detail and tell you some properties of it, but I will also show some recent developments which we came up with this year. Yeah, so what do I mean by explainable AI? I mean this very specific problem. So we have an input to our AI model, to our neural network, for example, an image, and it gets classified, and we want to explain why it was classified in this particular way. So we want to understand which input features, which input variables were important for this, were relevant for this classification. Here you see image of a pool table classified as pool table, and the shape of the table is quite important for the neural network to classify this image as pool table, but also the feet of the table are quite important. So we want to compute these kind of explanations. And of course, I mean, many methods have been proposed in the past. This is just like some snapshot some while ago. It's not up to date. I think now we have many more methods. So the big question is which one to choose? How do we compare them? How do we know that our method is good? How do we evaluate quality? And we will get a bit into this today in my talk. Another question is, I mean, can we learn more about the classifier? So we have explanations for individual samples, but can we deduce from it some knowledge about the general strategies of the classifier? Can we say something about the general strategy to classify pool tables? And I will show you very briefly today some approach to do so. Another important question, especially for practical applications, what to do with these explanations. I mean, you can look at them, you can verify that they make sense, but can we do something beyond? What do we learn about the classifier? What do we learn about our data? About the prediction strategies. So I will give you some examples on that. And a very recent development is explaining beyond classification. So for example, in machine learning, there are many models which are not classifiers. Like you have clustering problems, you have segmentation problems, you have outlier detection problems, and can we introduce a concept of explanation also to these kind of problems? And I will show you one example to do so for clustering. Okay, so let's start with the methods. So I very broadly categorized recently proposed methods into 4 categories. Of course, this is not a complete picture of the proposed literature, but it will give you some intuition that what types of methods we have today. So they are perturbation-based approaches which try to evaluate the importance of pixels, of inputs, by measuring how the classifier, how our neural network reacts to changes in the input. So for example, if you mask certain parts of the input, does it affect the classification or not? Another class of methods is, I called it function-based. So this classical methods, if you would ask maybe a mathematician how to evaluate importance, you would answer, okay, we can regard our neural network as a function, and for a function we can compute the gradient, we can compute sensitivity values, we can approximate the function using Taylor decomposition. So this is the functional perspective of explanation. The third one, which I will not cover here, but which is also, I think, quite popular, is this sampling-based approaches, or where you try to approximate, you prediction locally. So you need some kind of computation, so they are kind of computation heavy, or they can be computation heavy, but this is also like one specific class of methods. And the fourth class where our approach, layer-wise relevance propagation, falls in is, I called it here, structure-based explanation. So these approaches use the structure of the model to explain. So they use, for example, the inner structure of a neural network to explain the prediction. And I will show you that this gives an important advantage to these black box methods. Okay, so I will, like, from each of these categories, I will just like present some approaches and then very briefly discuss some of its weaknesses and advantages. So perturbation-based, very simple occlusion-based approach. So I think it has been around for many, many years. So people try to like understand the importance of certain features by masking parts of the input. For example, here we have an image of a castle, and you would then measure what happens if you would mask part of the image, what happens with the prediction. And you see that in the first two cases, it's still classified as a castle. So from that you could derive these areas are not important for the classification. Whereas in the lower case, if you mask the castle itself, it may not be classified as castle anymore. So you could derive that there is some important information for the class. However, if you think about it more deeply, this kind of simple approach has some major disadvantages. It's kind of slow, so you have to like mask different areas in the image and measure the reaction. It assumes some kind of locality, because it can be that not like one single area in the image is important for a class, but maybe the co-occurrence of two areas. So then you would have to use two different windows and mask things at different positions, and that would be like infeasible if you would think it wouldn't scale, at least for this simple approach. And of course, you may also, in the masking process, you may also introduce some artifacts. So assume you would, instead of using this mask which has this dots on it, you would use a gray window, a gray square. If you would mask the castle with a gray square, maybe it would still be classified as a castle, because a gray square on a hill looks like a castle. So like the way you manipulate the input may introduce some artifacts. So although this method is still around, in some communities people still try to understand the importance of input features by looking at the reaction to these occlusions, I wouldn't recommend it. Another simple approach, like a very maybe mathematics well-known approach to approximate a function, is Taylor decomposition. So if you say, okay, my neural network is a complex function, and I want to find some approximation, like first order approximation, so that I have I can like measure the importance. So this Ri is the importance of every input dimension, of every pixel for the prediction. For that, you can do that. That's a valid approach. But for that, you would need to find some good root point. So this x tilde. Because if you approximate a function, you always need a root point around you approximate. And this is the major disadvantage and difficulty of this very generic approach. That it's very hard to find a good root point in image space, in high-dimensional spaces. Because you want your root point to be close to your input, to your image, but at the same time, it should not contain the class discriminative information. So it's very, very hard to find these root points. Therefore, this doesn't like really give good explanations. At least if you cannot find a good root point. You can try to search for a good root point, but then you also have the problem that it's computationally very inefficient. So an approach which kind of generalizes these two, the perturbation-based and also the Taylor expansion-based, is gradient times input. At least for some simple functions, you can show that that the approaches which I presented before kind of reduce to gradient times input. So the idea is that you compute like your explanation by computing a gradient and multiplying it by the input. So you don't need any optimization. You don't need to search for any root points. You just have the explanation in one pass, one backward pass. You just need to compute the gradient, which is good, I think. But unfortunately, the explanations, if you see it here, are not very reliable. They are quite noisy, at least for these big neural networks which we use today. So here the classification decision was baseball, and it's very noisy explanation, doesn't really give you an explanation what you would expect. And the reason why gradient times input is not very reliable is twofold. One is that if you just compute the gradient, or at least the reason why in general gradient-based explanations are not very reliable is that they are very local. So they just tell you what would change your classification if you would change something in the input. It's very hard, they don't measure global effects. And another problem is, especially in deep neural networks, is the called scattered gradient problem. So people have shown that in deep neural networks, gradients become very uninformative. Or you have like you have some discontinuities, and therefore like you have, and these discontinuities are kind of mainly responsible for this noise. So the particular gradient value becomes more and more uninformative with number of layers, with the depth of a neural network. So although gradient times input has some good properties, it's fast, so you don't need to optimize. It has this gradient problem. So gradients are problematic for deep networks. And our approach, which is a structure-based approach, layer-wise relevance propagation, proposed in 2015, was kind of one of the first explanation methods for deep neural networks and beyond. And to some extent, it solves the problems which I mentioned before. So the idea is to use structure to simplify the explanation problem. So instead explaining the whole thing at once, the very complex function, the very complex neural network. So the main insight of LRP is that neural networks are kind of compositions of simpler functions. So at every layer, between every layer, you have a ReLU function, which is a relatively simple function. So instead of explaining the whole thing at once, which can be very hard, LRP kind of does a divide and conquer idea. So you explain, you kind of decompose, you explain the easier functions, and then we can show that we can aggregate this information in a meaningful way. I will tell you a bit more in a few slides why this is possible. But the intuition for you is that by using structure, we can simplify the explanation problem. And therefore, LRP is more reliable than some of the methods which I presented before. Okay, first I would like to give you some intuitive walkthrough how it works. And then we'll come back a bit to the hard math, and I would tell you, I will give you some intuition why this divide and conquer idea is possible. So the idea which we had is we wanted to decompose the classification, the predictions. We wanted to say, okay, let's decompose the prediction value f of x let's kind of decompose it as a sum of relevance values. And every input, every pixel should have a relevance value assigned. And the property should be that the sum of these relevance values match the prediction. And this relevance value should measure how much this pixel, how much this input contributes to the prediction. How much it contributes to the prediction. And how can we do this? How can we compute these relevance values? So first, we do a classification pass. We classify the image. It's a rooster. This is a classification output. And some of these intermediate neurons get more activated than others because they encode something. They encode certain shapes which are related to this image. So maybe this one neuron encodes something which has to do with the rooster's head. Maybe this one encodes something which has to do with these flowers. And maybe this one, which does not get activated, encodes something which has to do with the category cat or dog, but not with the rooster. So we know that neurons, certain of these neurons kind of encode specific things. And we can, if we classify, we can measure these activation patterns. And the idea which when we want to explain is, we want to redistribute this prediction output. We call it the total evidence for the rooster. This value gives us how sure the network is about the rooster in the image. We want to redistribute it back to input space, layer by layer. So in the first step, we want to redistribute it to the next lower layer. So from here to here to here to here to here. And how do we redistribute it? We want to redistribute it in a way so that this neuron gets an appropriate share of the relevance, and this one gets an appropriate share of the relevance, and so on. So the simple LRP rule, which we proposed, kind of tells us that there are two factors which should be considered. So the one factor is the activation of the neuron, xi. So if this guy is more activated, it should get more relevance because it encodes something which is related to the image. This is the intuition, xi. And wij, the connection between these two, tells us something about this. The parameter comes from training, so it tells us something like how these two are connected, and if they are like highly connected, then there should be more relevance flowing through this connection. If they're not connected at all, then there should be no relevance flowing. So we have these two factors, xi and wj, and we kind of proportionally redistribute relevance. This is the intuitive idea. Then we have some extensions to make things more numerically stable, which is called like epsilon LRP. So we, for example, for the denominator, we add some epsilon to make it numerically stable. Another rule which makes it numerically stable is alpha beta LRP. Here we redistribute things according to the same logic, but we do it separate for the positive values and for the negative values. We want to ensure that this denominator will not be zero, will not vanish. So these are like the two rules which we propose. And I will show you that these rules are related to the concept of Taylor decomposition, deep Taylor decomposition. Okay, so if we redistribute from here to here to here to here, we have in the end some relevance in the input neurons, which we can then visualize as a heat map. We can see that the rooster's head was particularly relevant for the classification. Okay, so I will very briefly walk you through this idea of Taylor decomposition, because I mean the algorithm which I presented here seems, okay, maybe it seems like a good idea, but it seems like very intuitive. There is no proof, there is no theory behind it. But actually we have some theory which I would very briefly like to walk you through, and then we will go to the applications. Okay, so this is like the simple Taylor approach which I presented before, which we had here, which we say it doesn't really work because it's very hard to find a root point, and also because we have this gradient shattering problem. So the simple Taylor approach, although being mathematically valid, because it's very nice to approximate your prediction in this way, the problem is that you don't have this root point. So it's very hard to explain the whole thing at once. But assume that you have already explained your function until here, and now you want to know how much relevance you need to redistribute from here to the next lower layer. Okay, and the idea, the trick here is that you can regard this relevance value as a function of the activations, because it only depends on the activations from here. So the relevance which you hear is a function of the activations. So what you can do, you can apply Taylor decomposition to that. So you can apply the same concept, but you will not do it in the input space between the whole thing, but you only explain things layer-wise. And actually it turns out that this function is very simple. So this relevance value is a very simple function of these activations. So you can use all your Taylor approximation machinery, which is there, and it's very, very easy to find the roots point because the function is very simple. And if you do that, you will arrive at the LRP rule. And depending on which root point you choose, and we argue that for different layers, it makes sense to use different root points, or root points with different properties. For example, if you want to redistribute your values to pixels, pixels usually have a box constraint. So pixels are between 0 and 255, for example. So it makes sense that your root point is also within this range. Therefore, for pixel values, we have like one type of LRP rule. If you think about Rayleigh activations, if you want to, they are always positive or 0. So you also have some restriction, and so you also may want to find a root point in this range. So anyway, so to make it short. To make it short, it's important to use the appropriate rules to each layer. So what we recently realized is that it makes sense to use different rules for fully connected layers and for convolution layers because they have different properties, as I said. And if you do it correctly, then your explanation will have good properties, and your explanation methods will work very well. Because sometimes people, I've seen a couple of papers recently that they say explanation methods do not work, gradient-based or this kind of explanation attribution methods are not discriminative or do not work. And this is because people use the wrong redistribution rules. So if you do it correctly, it works. And these redistribution rules, as I said, they are not like randomly chosen. They are not heuristically chosen. There is a clear mathematical model of how to choose them. So they're derived from this Taylor decomposition approximation. Unfortunately, due to time constraints, I will not be able to go into it deeper now. We can talk maybe afterwards. Still, I want to move to applications, but before that, I mean, we have to answer the question, like, which one to choose. I mean, I told you that LRP has some theory behind it, has some advantages, but you may want to know how to evaluate the quality of explanations. And actually, there has been a lot of work on evaluating explanations, quality of explanations. Because sometimes if I review papers, people write that there is no objective way to evaluate, therefore we don't compare to prior work. This is nonsense. There is a lot of work on how to compare, how to evaluate explanations. There is perturbation-based analysis method, which kind of measures the stability and the selectivity of explanations. People use also like axioms, which give you some theoretical properties. We have recently some work using a toy model and ground truth explanations. There is also like the pointing game. So there is a lot of different work on evaluating the quality, which should be considered. If you develop a new explanation method, you should compare to state of the art and at least using some of these quantitative measures. Okay, so let me go to applications. So we have applied LRP in various domains, not only for images, but also for speech, for text, for videos, for medical data. I know from other colleagues that they also apply it in their scientific fields, but also in the industry. People use this explanation method more and more. And we have also like applied LRP for different types of models. I think it should be different type of models. So LRP is kind of a concept which is very flexible, very generic. It's doesn't only work on neural networks, but it can be applied to support vector machines, to clustering algorithms, and so on. I will tell you a bit more about that later. Okay, so now I want to give you, I think, 4 use cases where we applied LRP and learned something. So the one is maybe the most spectacular one. So there was this Pascal VOC challenge. So Pascal was this European cluster network of excellence. They organized a very prestigious image classification challenge for almost a decade. And people always compared their methods. But at that time, they didn't know what their methods were doing. They were black boxes. They just compared the performance on a holdout data set. So they had the train data set for training the method, and there was the test data set for evaluation. And we thought, okay, let's look into that. What did the methods learn? And it turned out that the method like classified ships mainly based on the presence of water. So it didn't like really focus on the ship itself. The class train was classified very accurately, but not because of the train, but because of the tracks. And the class horse was even worse. So the network in most of the cases even didn't consider the horse, but considers a copyright tag, because many of the images in the data set had a copyright tag, many of the horse images. And you can't believe that thousands of people, high-class researchers, participated in this challenge for almost a decade, and nobody realized it. Because nobody looks at the data. If there's thousands, tens of thousands of images, you wouldn't go through all the images to check these kind of things. Another thing which we realized, which is maybe more also like some kind of artifact, but it's even harder to detect. Because if you would check the horse images, you would probably realize that there is a copyright tag. But here we trained a deep neural network, pre-trained on ImageNet, on some face data sets. So the task was to predict the age and the gender. And we see here is a heat map. The red color tells you like what speaks for the prediction. The blue color tells you what speaks against the prediction. And the prediction was in both cases correct. So this lady was classified 25 to 32, correct. for her, laughing is a feature which supports the prediction decision. This lady was classified 60 plus, also correct, but for her, laughing speaks against this classification decision. In other words, the network learned that old people don't laugh or laugh less. And you wouldn't see that, you wouldn't see this bias if you wouldn't have this heat maps, because the classification decision was correct in both cases. Because for this lady, there are many other features which speak for high age. So these other features kind of overvote the laughing. But and I think these biases, this non-representative data sets are everywhere, so we have to be very careful. Another thing which we did is we used LRP to understand the model. So we applied clustering on the activation features and visualized the representation. So we saw, for example, for VGG, the lower, which is kind of course, well known, but we really showed it. Here, the lower layers focus more on like more easy edges and textures in the scene, whereas the higher layer features focus more on like objects which are more complex. We also applied it to this Atari games of DeepMind, and if you focus here, you see that this part is important, and you will see in a minute why. So the network like really tries to play the game, plays the ball over there. Because it's a very safe strategy to play the ball there, because you can make a lot of points without risking to lose the ball. It's a very, very smart strategy, but by checking these explanations, we could see it like before the network was doing it. And we kind of also analyzed this behavior over training time. So on the x-axis you have epochs of training, and these different lines correspond to different objects. And you see the first thing the network learns is that the ball is an important element of the game, the green line, which makes sense, because if you lose the ball, you lose. Then the black line tells you this pedal is an important element of the game. And after some training, the network figures out that it's very good to focus on this tunnel, to build this tunnel. So you can study the development of strategies over time with this tool, at least for some applications. So we use this tool to analyze the predictions. We use this tool to analyze the model and its learning strategies. And we also use this tool to analyze the data. For example, in the sciences, and if you have brain data, it's not so much that you want to understand your model, you want to understand your data, because you want to understand the relations between different voxels in the brain or between different genes in a disease. And here we kind of trained a neural network to decode fMRI data, and with our tool, with LRP, we can kind of explain every fMRI voxel in this setup, which is quite cool. Okay, so I have to speed up a bit. Meta explanations, another topic. So as I said, what we have is we have like individual explanations, but assume you have millions of images, you wouldn't be able to go over all these explanations by yourself. So we thought, let's apply some clustering. Let's cluster these explanations. Let's compute them and cluster, and then we can see if there is some common structure. And actually, for this Pascal VOC data, we found for the horses we found some clear structure that in two clusters belong to the copyright tag here. This is images which are portrait, and this is like vertical images and horizontal images. One class of horse images where you try to where you have like this horse competition, and you have these wooden barriers, and another cluster which is maybe more mixed. And then the number of cluster elements, I mean, we use spectral clustering. So if you are familiar with spectral clustering, so you can just see like what is the eigengap between your eigenvalues, and then you can determine the number of clusters here. So we also applied it to more complex data. Recently, we applied it to ImageNet, and you also wouldn't believe that there is also some things which are fishy. But that's another paper, and maybe next time I will tell you about that. Okay, beyond explaining classifiers. So how would you explain, for example, k-means? Everybody uses k-means to cluster data, but how would you explain it, the result of k-means? So we thought that we know how to explain neural networks. Can we convert the k-means solution to a neural network and then explain it? And actually we can. We can reformulate the k-means, the clustering solution which found by k-mean or deep k-mean as a neural network. And then we know how to explain neural networks. So this is kind of the trick. We call it neuralization trick, neuralization propagation. And we proposed it for k-means, for kernel k-means, for deep k-means, and also for one-class SVM. And actually, with this trick, you can, for example, you can ask the question, like if you have a clustering, here you have a clustering of text documents, you can ask the question, why does this document belong to this cluster? Or you can ask the question, why does this document does not belong to the other cluster? So you can ask these kind of questions, and at least to our knowledge, this is the first time ever people tried or asked the question of explanation in clustering. So we think that this trick of neuralization can be also applied to other algorithms, and is a generic approach to explain machine learning algorithms. Okay, let me summarize. So the decision of machine learning methods of deep neural network is often complex, and analyzing it directly from input to output may be tricky, may be complicated. But luckily, neural networks have some layered structure, and layer-wise relevance propagation utilizes or leverages this structure to simplify the explanation problem. And there is a theory behind it. We have some proofs that what we do is valid. And you have to, if you apply it for your application, you have to be, it's important to use the right redistribution rules for the right layers. There is a recommendation in our recent papers. And we saw that these meta explanations can be done if you kind of cluster, if you apply some clustering to your individual explanations. And lastly, we saw that many ML models can be seen as a neural network, and therefore also explained as a neural network. So we have a lot of papers written about this. We have also some book which came out very recently, where this is not only like our work, but we did this with Andrea Vedaldi and Laskai Hansen, and we also invited a lot of other people to contribute. So it's like a very broad summary of current explanation, current state of the art in explainable AI. So we have not only like methods, but also like how to evaluate applications, and also some overview chapters. We have also like a website with some code and with some demos, and all our papers which I referred to are also on the website, so you can check it out. And I'm happy to take a couple of questions. Thank you very much.
Yeah, so the question is for Wojciech.
Yeah, thank you.
I think it can be both. I mean, so a question which we have on our minds for some time is, how can we use it? How can we utilize explanations to improve the model automatically or semi-automatically? I think this is a question which is very interesting for data scientists, right? You want to have better models or more reliable models. Therefore, I think you can use explanations for that. But of course, for the end users, it's like additional information which can be important to foster trust for verification purposes or for legal reasons. So I think it's both the end user and the engineer are our target audience. Okay, can you repeat?
Can you explain this neuralization?
This neuralization idea? Oh.
Yeah. How exactly?
I mean, this we derive for k-means, and for one class SVN, you would need to derive it for different algorithms. So there is no like one formula which works for all, right? So for clustering, what we wanted to approximate or rewrite is this function. And this is an indicator function which tells you, is kind of the evidence that a data point belongs to a cluster or not. And you can rewrite it in this way. But for different algorithms, it may be more complicated or it may not work at all. So this is a concept which I think can apply also to other methods, but you have to think about how to rewrite your algorithm that it can be represented as a neural network, which is not a trivial task.
Any questions? If not, I'll just say thank you so much for the answer.
Thank you.